And let's move to the second part of our session, which will focus on materials. Our next speaker is Pinaki Chowdhury, and he's a professor in the Institute of Mathematical Sciences in India. And he will give a talk about amorphous materials properties analyzed by means of large-scale computing.
So good evening. My name is Pinaki Chowdhury. I'm a physicist at the Institute of Mathematical Sciences, Chennai. And today, I thank the organizers for inviting me to speak at this very nice meeting. It's a great pleasure. So today I'll be telling you about the work that is done in the context of studying amorphous materials using large-scale computing. So by amorphous materials, we typically understand, for example, glasses. So window glasses is a very common example. But there are other categories of amorphous materials that we encounter in a daily life, mostly in the as soft matter. So for example, mayonnaise, ketchup, emulsions, paints, chocolate, then cosmetic cream, tar, snow, mud. These are all soft materials that we encounter in our daily lives, and all of these are amorphous materials. So what we mean by amorphous? Amorphous means that these are disordered. So if you look under a microscope, unlike crystals, which have a very organized structure of atoms, so the amorphous materials have a very disorganized structure of this atoms and molecules. And amorphous materials are not only like soft, as I gave some examples of paint, mayonnaise, ketchup, etc. They're also hard materials like metallic glasses, window glass, and so on. And the important property of all these materials are that they are rigid, that they can hold their shape. So you need to apply some force in order to deform them. So for example, in the case of mayonnaise or ketchup, you need to really shake the bottle in order to make the ketchup or the mayonnaise flow. The other interesting aspect of these materials is that the constituent particles, be it atoms or the sand grains, they are of different scales. So you can go from nanometric scale in the case of atoms to millimeter or centimeter scale for the case of concrete and sand piles and so on. So what is the aim of studying amorphous materials? Of course, to understand how these materials are formed so that we can design better materials, and then also to study the response under different kind of perturbations so that we can also then design materials with specific responses and so on. This has been a challenging problem for more than a century, and so far theoretical understanding has progressed quite a bit, but still we are not in the state of where we can completely understand the microscopic processes that lead to this kind of macroscopic behavior. Numerical modeling has helped us to a great extent in understanding or gaining physical insights into these materials. So what are the challenges that we face in numerical simulations? The biggest challenge is timescales. So, for example, a amorphous material or a glass is formed by cooling a liquid from high temperature to low temperature. So what happens is that as the temperature is lowered, the viscosity increases. So as you can see in the left side plot, the viscosity increases by orders of magnitude, like 16 orders of magnitude, until it reaches a value of 10 to the power 12 poise, at which a glass is said to form. So this involves very enormous timescales of relaxation within the system. A classic example of this timescales involved is this pitch tar experiment that's going on in New Zealand since let's say last 90 years or so, and they're counting what is the time between the time between two droplets that fall on the floor in this experiment. And what they measure is that each drop, the interval between each drop could be several years. So you can imagine the time scale of flow of these kind of materials. Unfortunately, numerical simulations with conventional algorithms don't allow to still reach scales yet. And only more recently, smart algorithms have been able to achieve states which correspond to relaxation timescales of this order. So large timescales is a big problem in the physics of amorphous materials. The next problem is complexity. So what do you mean by complexity? So the energy of any material can be written down as a function of its quark. So if you are in 3 dimensions and you have n particles. So then this function so the energy is a function of these 3 n variables. So you have this energy which is governed by this 3 n variables. So there's a energy landscape which is spanning this high dimensional space. So in the case of crystals, you have only one single minima in this energy landscape. On the other hand, for amorphous materials, this is a very rough landscape and with a lot of minima. And if you want to build this landscape for any material, so you have to optimize this function over this number of variables, which becomes an impossible task. So this complexity of the problem is a very difficult task to handle, even within the numerical schemes that we have today. The other problem is, of course, a problem of materials that all material scientists face. Is a multi-scale problem. So, for example, here we have the case of a fracture in a metallic glass. So this is a macroscopic phenomena having in millimeter scale. On the other hand, we would like to understand this phenomena from a macroscopic scale, from the physics of atoms and molecules and so on. And there are different interesting features that are happening even at micron scales and millimeter scales and so on. So how do we develop the physics of macro scale from the microscales? This is, of course, a challenging problem in material sciences, and this multi-scale problem needs to be addressed. And of course, this is a dream problem for all physicists, but of course, we are far away from resolving this entire scales from microscales to macroscales. So, so large-scale computing is necessary in this context, and to tackle this large time scales and large length scales. So, and if you want to study the time evolution of this large system over this large time scales of observation, then of course you need to handle large data, which is again a problem. So the simplest thing that you can do is to study model systems, which could be at the atomistic scale or the mesoscale. So I mainly work on atomistic models, so some results from atomistic models, and I'll also tell you a little bit about mesoscales at the end. So in the case of atomistic, you are just solving Newton's equations of motion, which we know from school. But of course, we are solving Newton's equations of motion for 1 million particles, for example, which are interacting among themselves. So this becomes a large-scale problem, and you need to take course of parallel computing in order to do an efficient work at this. So the problems that the physical problems that we're interested in is, of course, how to get the macroscopic behavior from the microscopic physics. We can test theoretical ideas or different hypotheses to see if they're correct or not. We can perform thought experiments. Not all, in the labs, not all experiments are possible, so you can do different kinds of experiments in this using computers, and then you can see which experiments can be translated to the lab and so on. Of course, then in this process, we explore new phenomena and with the hope of designing new materials. So what I'll do is I will tell you about 3 or 4 problems that can be done with this large-scale computing, and then at the end, I'll tell you something about my micro-meso modeling and so on. So what we'll be first tell you about is non-equilibrium gelation. So gels are something that we know in our life, so in toothpaste and shampoo and so on. And so in one class of gels are formed by quenching a liquid from high temperature to low temperature. So a uniform liquid goes from a liquid goes from a spatially uniform state to this phase-separated state when you quench from high temperature to low temperature, because you are quenching into this 2-phase separation region. And on the left-hand side in the panel A, you see a structure of a gel, which is this kind of network kind of structure that forms. So experimentalists had been puzzled about this formation of these kind of structures, and also not only the structures, but also some very fast time scales that they could observe in these experiments. And the question was, what is the origin of this fast time scales when I'm doing a quench from high temperature to low temperature? So we did some numerical modeling. So we took some generic gel former, which shows morphologies which are very typical to gels and so on. And so here is a movie that I would like to show you to see what is the origin of this fast time scale. So what you will see here is that the black particles are the material particles, and the white is basically the gas. And what you will see is that because of thermal fluctuations, there will be sudden rupture in this network, and then it will show a elastic recoil and so on. I hope the movie plays. Yes, it plays. And so you can see that there is a rupture process, and then it there are fragmentations happening at different points. So this rupture process leads to this very fast time scale. So in this case, with using 2 million particles, we are able to show this able to get insight into these fast processes that are there. Basically, that spontaneous ruptures are happening inside the system due to thermal fluctuations, and these lead to long-range elastic decorrelations and so on. So then I'll tell you a couple of problems we use where we are studying to mechanical deformations and so on. So one problem is the physics of cavitation. So what do I mean by cavitation? So for example, in solids, if you are expanding the solid by any means, by applying a force or pulling it at a certain, then holes show up in the solid, show up inside the solid, and these are precursors to fracture. So you can do this kind of experiments also in the computers, and but in order to look at this phenomena, you need to use very large systems. For example, 1 million particles again, and when used in this case, GPUs to do this kind of simulations. And so when you do this kind of expansion process, what happens is that if you look at the pressure versus density plot, the pressure drops inside the system, it gradually drops, and suddenly there is a burst of pressure and a cavity opens up inside the system. So we are able to reproduce the phenomenology of cavitation inside the system. And if you continue with the expansion, more and more cavities emerge, and this leads to the eventual failure. So again, a physical process, a realistic process, we're able to reproduce in the computer, and by reproducing this phenomenology, we are then able to look at the microscopic processes that lead to this kind of cavitation and failure and so on. So then the other mechanical problem looks at is the response to shear, for example. So here you're applying some kind of deformation to the glass, which is basically you are trying to shear it like this, and then you are seeing how the system responds. So the upper panel corresponds to a colloidal glass, and where we see that at some point in the deformation process, some part of the system is flowing faster. The red particles are flowing faster than the green particles. So basically a shear band has formed inside the system, so there is a region which is moving faster than another region. And these shear bands are also seen in not only in colloidal glasses, but also in metallic glasses, which I show at the bottom panel. So in both the bottom panels, you see shear bands forming in metallic glasses. And these are again precursors to fracture and so on. And we can do this kind of numerical experiments. So you can take the solid and then you can deform it. And again, you can reproduce this kind of shear banding phenomena. And you can see avalanches that lead to this kind of shear banding and so on. So these are particulate simulations or microscopic simulations that one does use. Even by using this kind of million particle simulations, you are only able to get access to about 100 atomic diameters in length in the cubic box and so on. So you are far away from the macroscopic scales and so on. So you have to take another step, that you have to couple your microscopic simulation to something mesoscale and so on. So what do I mean by mesoscale? I just skip this slide. So this is, for example, an experiment of foams. So a microscopic scale corresponds to the bubbles. The macro scale corresponds to the entire experiment, and the mesoscale would be some intermediate length scale over which you will coarse grain your variables and come up with a new description and so on. So, as I said, the microscopic correspond to these particulate simulations that I talked about earlier. The mesoscale simulations would correspond to some simple lattice model over which you will look at the time evolution of these coarse grain variables, and then of course there's a macroscopic scale which corresponds to the evolution of the macro variables like density and so on and so forth. So this is a typical mesoscale model that many people are studying. So here the quantity of interest is this coarse grain stress. And then one writes down the equation of motion of the coarse grain stress, which is evolving in time inside the system due to the external deformation that is happening. The important part is the second term in this equation of motion that is written in the pink box. So this allows for non-local coupling between different lattice sites due to the events that are happening at any point and so on. So what we have been able to do very recently is that we have been able to couple a microscopic simulation to a mesoscale model. So what we do, we measure we do coarse grain measurements in this microscopic model. We feed these coarse grain measurements into the mesoscale model, and then we run them parallelly to see whether the mesoscale model reproduces the microscopic simulations or not. And indeed, both for steady state response as well as for transient response and for different deformation protocols, we have been able to demonstrate that the microscopic model and the mesoscale model match very well. So in other words, we have been able to do a successful translation from microscopic modeling to mesoscale modeling, which can be the building block for more large-scale mesosimulations and so on. So within this very short talk, what I've been trying to emphasize is that understanding the properties of amorphous to study systems over long time scales and across wide length scales. And this is a challenging problem. And numerical modeling and large-scale computing is very useful in this context to gain physical insights into the phenomena that are happening. But we are still limited with the computational capacity that we have and only can study length scales, which are of few hundreds of diameters or atomic scales and so on. And so we need to develop next generation micro-meso models to bridge across scales. And this is what we have been starting to work on. And there is some project which is funded by the National Supercomputing Mission in India. And we are a partner in that project. So thank you for your attention.